Okay, so we're going to prove an interesting statement which has to do an integral of this form. So if you have a decreasing sequence of numbers, of positive numbers, a0, a1, a2 up to an, which are all positive, technically it doesn't matter that a1 through an is decreasing, but it just matters that a0 is the largest one. And you have this condition that a0 is greater than the sum of the other terms of the sequence. Then the integral of this product, and just a reminder of what this product notation is, it's like the sum, where you plug in like whatever values for k from 1 to n for everywhere you see a k in this expression, and then you multiply them all together instead of adding them all together. So expanding out this product, it looks something like this, where you have sine a0 over a0x, sine of a1x over a1x, sine of a2x over a2x, all the way up to sine of a n x over a n x. So if you have these two properties, then it turns out that this evaluates to a pretty simple expression. It's just equal to pi over 2a0, where a0 is your largest term. So it's pretty interesting because, for example, you can look at the integral from 0 to infinity, sine x over x, sine x thirds over x thirds, sine x fifths over x fifths dx. And what you have here is that the terms are 1, 1/3, and 1/5. And the sum of 1/3 and 1/5 is 8 over 15, which is certainly less than 1. And so you have that your largest term is 1, which is your a0. So this will evaluate to just pi over 2. And if you throw in another term in here, for example, say sine of 9x over 10 over 9x over 10 dx. So 1 is still your largest term, but if you add up these other three terms, 1/3, 1/5, and 9/10, those are obviously going to add up greater than 1. So this is not necessarily pi over 2. But then you can throw in another term, say something like sine of 10x over 10x. Now 10 is your largest term, and your other terms are 1, 1/3, 1/5, and 9/10. And if you add up those four numbers, that's obviously less than 10. So this integral is going to evaluate to nothing more than pi over 20, since your a0 is your 10, which is your largest term out of these 5 numbers. So to prove this, we're going to take a couple steps. And the first step will be proving or solving what is called the Dirichlet integral, which is the integral from 0 to infinity of sine x over x dx. So this integral is interesting in its own right. So in some calculus classes, like you'll be asked to prove if an integral converges or diverges without having to actually compute its value. So one of the easiest ways to figure out if an integral converges, if it works, is by using this sort of trivial bound. So what you do is you essentially take the absolute value of what's inside, so sine x over x dx. And so what this does is just takes sort of the cumulative of all the absolute value of the function. And this integral, it turns out it diverges. And if you take the integral of 1 over x, then that diverges. And it turns out that the sine of x is not small enough to be able to control the 1 over x to make it converge. So the absolute value of, if you take the absolute value of the inside, the integral turns out to diverge. But this integral converges, which means that the negative parts of sine x cancel out with the positive parts to somehow make this converge. So this is an example of an integral that isn't absolutely convergent, but it is still convergent. So one way to evaluate this is to notice the following thing. If you take the integral from 0 to infinity of e to the minus xy dy, so what we're doing here is we're taking x to be a constant number, say like 2 or 5, and we're introducing another variable y. So if we evaluate this integral, it's pretty easy to see this minus e to the minus xy over negative x from 0 to infinity. And so this is just because if you differentiate the top, this is just e to the power of some constant times y. So if you differentiate with respect to y, you just bring out the constant, which is negative x. Then the negative x's cancel and you get back this thing. And so evaluating this, if x is positive, which is what we'll be considering, then, because this integral goes from 0 to infinity. So if x is positive, then this exponent is e to the power of minus infinity over negative x. So this is like e to the minus infinity over negative x infinity. And e to the power of negative large numbers very quickly goes to 0. And if you plug in y is equal to 0, then this numerator will become e to the power of 0, which is 1. And then the denominator will just be negative x. And since it's the lower limit, you subtract it off. So this is minus 1 over negative x, which is equal to 1 over x. So now what we'll do is we'll sort of take this way of writing 1 over x, which it seems to overcomplicate our problem, but we'll put that into here and it actually simplifies it. So we'll rewrite this as the integral from 0 to infinity of sine x times the integral from 0 to infinity of e to the minus xy dy dx. Okay, so what we're doing here is we're just taking this expression which evaluates to 1 over x, and then we're writing this in, and since sine of x is just sine of x, we're writing that out. So we're integrating with respect to y first and then with respect to x. So since sine of x doesn't depend on y, it's a constant for this integral, so we can sort of move that in. And we have that this is the integral from 0 to infinity of sine of x e to the minus xy dy dx. Now, this integral turns out to converge well enough. I won't go into too much of the details, but you can switch the order of integration. You can integrate with respect to x first and then with respect to y. So if you look at the bounds of integration, x goes from 0 to infinity and y also goes from 0 to infinity. So if you sort of graph out the two-dimensional plane, you're integrating over this region. So switching the bounds isn't that much of an issue either. So this just evaluates to the integral from 0 to infinity sine x e to the minus xy dx dy. Okay. So now here, in sort of an introductory calculus class or whatever, you might get this inside integral as a sort of exercise for integration by parts. And it's interesting because you can solve it by integrating by parts twice, and then you move everything over to one side and then you solve it out and you get a nice answer. But there's actually, in my opinion, a cleaner way to do this, and that's by using Euler's identity. So that is e to the power of ix is equal to cosine x plus I sine x. So here what we have is a sine x, and we want to kind of use this exponential to evaluate our integral. So what we can do is you can take the imaginary part of both sides, so that pretty much gives you the imaginary number, the imaginary component of a complex number. So here we see that the coefficient of the real part is cosine and the coefficient of the imaginary part is sine. So this will just be sine of x. So that means that we can rewrite this integral as double integral 0 to infinity of the imaginary part of e to the ix times e to the minus xy dx dy. Okay, so now since e to the minus xy, since x and y are both real numbers, e to the minus xy is also a real number, and if you scale up a constant, if you scale up a complex number by a constant real number, then what you're doing is you are scaling up the real and imaginary parts by that number. So what that means is that the imaginary part of a real number times a complex number is just the real part times the imaginary part of the complex number. Essentially what I'm saying is that you can move this e to the minus xy to the inside because you're just scaling up the complex number. This is the same thing as the imaginary part of e to the ix, e to the minus xy, dx dy. Okay, so now what we want to do is we want to integrate this part, but we have an imaginary part of that, so that's not too nice. So if you remember like how we define the integral, it's sort of like a continuous version of a sum. And so if we add up complex numbers, we know that the sum of two complex numbers, you're adding up the real components and you're adding up the imaginary components separately, and then you put them together. So what that means is that the imaginary part of the sum of two complex numbers is the sum of their imaginary parts. So essentially, if you generalize that to integrals, what that means is that you can switch around the integral and the imaginary part. So this is integral from 0 to infinity of the imaginary part of the integral from 0 to infinity of e to the ix, e to the minus xy, dx, dy. Okay, so all we did here was we switched around the integral and the imaginary part because the integral is sort of a generalized sum. So we'll move this up here and keep working. Okay, so now we want to evaluate this integral. So we can rewrite this exponential as e to the power of ix minus xy. That's just combining the two exponents together. And then you can also factor out an x. So this just becomes e to the power of x times I minus y. So now what we have is e to the power of x times some constant, because for now y is a constant. And we're integrating with respect to x. So what we have is just e to the power of a constant times x divided by that constant. So if we rewrite this up here, this is equal to the integral from 0 to infinity of e to the power of x times I minus y, imaginary part of all this, divided by I minus y, evaluated from 0 to infinity, dy. Okay, so now what we want to do is sort of expand out this e to the power of ix minus y to sort of see easily what this will be. Yeah. So if we write out e to the power of x times I minus y over I minus y, we want to do two things. First, we rewrite this as e to the power of ix e to the power of minus xy. And what that allows us to do is rewrite e to the power of ix as cosine x plus I sine x. So this is e to the power of minus xy cosine x plus I sine x. And then the other thing we want to do is get rid of this imaginary denominator. So we can do that by rationalizing it. So we multiply it by negative I minus y, and then the numerator also by negative I minus y. So negative I minus y, and then divided by. So now what is this going to evaluate to? We can do it out, the algebra out, and simplify this stuff. But there is an easier way to see what that evaluates to, and it's like this. So you can imagine the complex numbers. So this is your real part, this is your imaginary part. And so the number I minus y, the real part is negative y. So that'll be somewhere like here. And then your imaginary part is 1, right? And so we know that if you multiply a number by its complex conjugate, you're gonna end up with the magnitude of the number squared. So the magnitude of this squared is just y squared plus 1 by the Pythagorean theorem. So the denominator then evaluates to y squared plus 1. And so our goal is to evaluate this from 0 to infinity. So I'll rewrite this integral part up here. Okay. So as x grows really large, e to the power of minus xy will go to 0. And cosine of x and I sine of x will both be bounded by 1. So by, sandwich theorem or whatever you want to call it, at the upper limit as x goes to infinity, this term will just go to 0. And as x goes to 0, what will happen is you get the integral of 0 to infinity of the imaginary part of, so you put a negative sign because it's the lower limit. E to the power of 0 times y is e to the power of 0, which is 1. Cosine of 0 is 1, and sine of 0 is 0. So this part will also evaluate to 1. So this whole expression becomes 1. And then you are left over with this negative I minus y. Okay, so now you have a negative I minus y at the top. So you can just turn them all into pluses. And now it's pretty easy to see y over y squared plus 1 is the real part of this complex number, and I over y squared plus 1 is the imaginary part of this complex number. So the imaginary part is just the coefficient of I, which would be 1 over y squared plus 1. And so we can use that to say that this is the integral from 0 to infinity of 1 over y squared plus 1 dy. So now this is one of those integrals that you should be pretty familiar with. This is just the arctangent of y. So the arctangent of infinity, you can think about it this way. As you increase your angle to pi over 2, the tangent of your angle will increase to infinity. So the arctangent of infinity is pi over 2. And then the arctangent of 0 is 0 because tangent of 0 is 0. So what you get is that this evaluates pi over 2, and then that proves our Dirichlet integral, that this integral is equal to pi over 2. So I'll clear the board, and then we'll get to the next steps of this proof.